All right. Now, in the last lecture video, we looked at how to calculate probabilities of events in those situations where the experiment has been conducted in such a way that the sample space of that experiment consists of equally likely events. Now, in that kind of a situation, the way that we calculate the probability of an event is to determine or count the number of ways that the event can occur. We also determine or count the number of ways that the experiment can end up. And then we calculate the ratio of those two values, the number of ways that the event can occur divided by the number of ways that the experiment can end up. And that is the probability of the event in that kind of a situation. And so it's going to be beneficial for us if we have ways, convenient ways of counting the number of ways that things can occur. And so in this lecture video, that's what we're going to be looking at. We're going to be considering three counting techniques that are useful for computing probabilities in the context of sample spaces with equally likely events. Now, there are three counting rules that we are going to utilize. There are more counting rules than this, but we're going to get a lot of mileage out of these three counting rules. The first one that we'll consider is the fundamental rule of counting. After that, we will look at how to count permutations or arrangements of objects. And then finally, we'll look at how to calculate combinations of objects or subsets of objects. And then in all of this, we're going to be combining these different rules based on a particular problem. So let's first look at the fundamental rule of counting. So suppose that a process or procedure consists of k steps such that step 1 can be performed in a number of ways that we'll denote by n1. And then regardless of how step 1 was performed, step 2 can be performed in a number of ways that we'll denote by n2. And then regardless of how the first two steps were performed, step 3 can be performed in a number of ways that we'll denote by n sub 3, and so on. And then finally, regardless of how any of the previous k-1 steps are performed, the final kth step can be performed in n sub k ways. So when that's the case, the number of ways that the process or procedure can be performed is equal to the product of the number of ways that each step can be performed. So that is the fundamental rule of counting. So let's look at an example. All right, so let's suppose that a mathematician has 5 different shirts, 3 different ties, and 4 pairs of slacks. How many ways can the mathematician wear a shirt, tie, and pair of slacks without wearing the same exact outfit more than once? Now, we can think of putting together an outfit as a 3-step process. The first step, we're going to select a shirt. That can be done in 5 ways because there are 5 shirts available. Step 2 is selecting a tie. There are 3 ties to choose from, so that can be done in 3 ways. And then finally, regardless of the shirt or the tie selected, all right, step 3 is selecting a pair of slacks. All right, and because there are 4 pairs of slacks, this can be done in 4 ways. And so by the fundamental rule of counting, the number of different outfits is equal to the product of the number of ways that each of these 3 steps can be performed. So 5 times 3 times 4, or 60 different outfits. And so that mathematician can go for about 2 months, all right, and never wear the same outfit more than once. Here's another example of the fundamental rule of counting. A salesman, starting from his own city, must visit n other cities, each exactly once, and then return home. The distances between cities is known. The problem is to find an order in which the salesman should visit the cities such that the total distance traveled is minimized. Now, in general, this problem is known as the traveling salesman problem, and it's a difficult problem to solve in general. But we're going to look at just a small piece of this problem, specifically, how many ways are there to visit the n different cities? Now, an ordered list of cities to visit will be called an itinerary. And so we can think of setting up an itinerary as an n-step process because there are n cities to visit, each exactly once, where the kth step in that process corresponds to choosing the kth city to visit. And so step one would be choose the first city to visit, which can be done in n ways because there are n cities. Step two, choose the second city to visit, and that can be done in n minus 1 ways, regardless of how the first city is visited. Step three is choose the third city to visit, regardless of which two cities are visited in the first two steps. There are n minus 2 ways to visit that third city, and so on. Step K in this process would be choose the kth city to visit. This can be done in n minus k plus 1 ways. And then finally, step N, choose the last city to visit, and that can be done in one way. Once the first n minus 1 cities have been visited, there's only one more city to visit, and that can be done in one way. And so by the fundamental rule of counting, there are n times n minus 1 times n minus 2 and so forth down to 1. And when you multiply that out, that's n factorial. There are n factorial different itineraries for visiting the n cities. Now, the factorial function increases pretty quickly, and that's one of the reasons why the traveling salesman problem is difficult in general to solve, because as the number of cities increases, the number of different possible itineraries to consider increases very, very quickly. So even if you're using a computer, all right, and if you plugged in the distances between each pair of the n cities, even if you're doing a search amongst all the itineraries, to find that itinerary that has the minimum distance traveled, it can be quite difficult to do. In fact, it's not hard to come up with a problem where you can't actually solve it with a computer by enumerating all the different itineraries because the number is just too big. So that was the fundamental rule of counting, and you can see that it's fairly straightforward to use. The next counting technique we're going to look at is how to calculate or count permutations. And so suppose we have a collection of n distinct objects. The number of permutations, and now the word permutation is just a fancy word for arrangement. So the number of permutations or arrangements of R objects taken from the potentially larger set of n objects can be constructed that can be constructed from the set of n objects. Well, number one, we have to have some notation that we're going to use to denote this quantity and this count. And so this is the notation that I'll use in these notes. You might see slightly different notation in other references. All right. But this notation right here is going to represent the number of permutations of n objects taken R at a time. And the expression, we have a nice expression for that count, that number. It's going to be equal to n times n minus 1 times n minus 2 times and so forth down to n minus r plus 1. And another way to express that and to calculate it is to calculate the ratio n factorial over n minus r quantity factorial. So that gives us the number of ways to arrange n objects taken R at a time. So for example, we could have 20 objects that we want to arrange, but that we have to select from, but we're only going to arrange 12 of them at a time. And so that the number of ways to do that would be 20 permute 12. Now let me just show you, there is some functionality that will implement these formulas that exists on the TI-84 calculator, and these formulas or these functions also exist on the TI-36X Pro. So if you have either of those two calculators, then the menus here should look the same, and so you should have this functionality. And I believe that the Casio calculators also have this functionality. So the first thing you would do is press the Math button on the TI-84, and when you do that, you're going to get this menu of math functions or math functionality on the calculator. And then what we would do is we would uh, select the prob or probability menu option. All right, and so when you do that, then you get this submenu, okay, and you can do various things here. We're interested in the context of counting techniques. We're interested in submenu options 2, 3, and 4. So in the current situation, we're looking at the number of ways to permute n objects taken R at a time. And you can see here that the notation that I'm using in the notes is equivalent to the notation that's used on the menu of the TI-84 calculator. So that's one of the primary reasons that I'm using that notation, to make it consistent with the calculator notation. Okay, so we have this nice formula for counting the number of permutations. How did we come up with that, or how can we come up with it? This is a theory class, and so that's one of the things that we're interested in here. We're interested in more than just the formulas. We're interested in how we get those formulas. And so let's see if we can derive this formula for ourselves. So consider the process of constructing such a permutation. Now, there are n ways to select the item for the first position in the permutation. Now, let me just stop here and say that when we think about constructing a permutation of R objects, or of n objects taken R at a time, think of R slots that we have to fill. Now, if we were in class in person, I would probably get up on the board and draw some things on the board. But imagine me drawing drawing R lines or slots on the whiteboard. Okay, and in each slot, we're going to, in each position, we're going to put one of the things to be arranged. So we can think of constructing a permutation as an R-step process. So the first step in that process is to fill the first slot. Okay, and that can be done in n ways because we have n objects to select from. Now, regardless of which item was selected for the first position, to fill that second position, we've got n minus 1 objects to select from. All right, so n minus 1 ways to select an object to put in that second position. Now, regardless of which items are selected for the first two positions, there are n minus 2 ways to select the item for the third position in the permutation. All right, and so we continue on in this way. And so in general, regardless of which items are selected for the first k minus 1 positions, there are n minus k plus 1 ways to select the item for the kth item in the permutation. And then applying this result to the last position in the permutation, the rth position, we see that regardless of which items are selected for the first r minus 1 positions, there are n minus r plus 1 ways to select the item for the rth position in the permutation. And so by the fundamental rule of counting, the number of permutations of n objects taken r at a time, right, this quantity here, is equal to the product of the number of ways that each step in that process can be performed. So n times n minus 1 times n minus 2 and so forth down to the last term, which is n minus r plus 1, right? And we can conveniently express that, instead of this long product, we can express that as n factorial divided by n minus r factorial. Now, I want you to convince yourself that this is actually the case. If you write out n factorial and write out n minus r factorial, then you'll see the terms cancel, and you get exactly this product right here. So what we're doing is appealing to this first counting rule that we looked at, fundamental rule of counting. And we're utilizing that to prove or to derive the number of permutations of n objects taken r at a time. So that is the number of ways that we can construct a permutation. And so it follows that this is the number of permutations of r objects taken from a set of n distinct objects. Now, sometimes we want to permute all n objects. All right? In other words, we want to permute n objects taken n at a time. And so utilizing this formula, right, this formula still applies. That would be given by n factorial over n minus n quantity factorial, or n factorial over 0 factorial. Now, just let me point out that the denominator here, 0 factorial, that is not 0. By definition, that is 1. All right? So it turns out that this is equal to n factorial. All right? And so that is the number of ways of permuting n objects taken all n, taken n at a time. So let's see an example of this. So a student has 3 math books, 4 reference books, and 5 history books. Now we're going to answer several questions, the first of which is, in how many ways can the books be arranged on a shelf? All right? So in how many ways can the books be arranged on a shelf? Well, there are 12 total books, and so we want to know how many ways can we arrange the 12 books on a shelf. Now, an arrangement is a permutation, and so what we're asking is, in how many ways can we permute or arrange all 12 books on that shelf? And so by the formula that we just derived, all right, that is given by 12 permute 12, and that is equal to 12 factorial ways. Now, this is the only step in the process of arranging or permuting the books on a shelf. If we're thinking about this as a process consisting of a number of steps, there's only one step, at least in the way that we're conceptualizing this, and that is to arrange all 12 books without any constraints. All right? And the number of ways of doing that is 12 factorial. Now, it turns out that 12 factorial is a pretty big number. I don't know what you might have thought this number would be, but it's 479,001,600. And so that is the total number of ways that 12 books could be arranged on the shelf. So is that larger than what you had thought? Okay, now this is a screenshot showing how we could calculate this on the TI-84 calculator and also on the TI-36X Pro. All right, using that menu option go to the math menu and then the probability submenu, and then I believe it was option number 2, all right, for permutations. And so we want to calculate the number of 12 permutations taken all 12 at a time, and again we get that same value. We can also calculate it as 12 factorial, and you can see that you get the same value. Okay, the second question, in how many ways can the books be arranged on a shelf if books of the same type must stay together? So again, we can think of this as a process involving one or more steps, and in this case, it consists of 4 steps. So step 1 could be the way I've got it set up here. Step 1 would be, let's arrange the 3 book types. So again, we've got math books, we've got reference books, and we've got history books. And so that first step is arranging the order of the 3 types of books. All right? And that can be done in 3 factorial ways because we're wanting to permute the 3 types all at once, all 3 at a time. Once we've arranged the types, then we're going to arrange the books within each type. And so step 2 would be arrange the 3 math books within its section. And because there are 3 math books, there are 3 factorial, or 3 permute 3 ways of doing that. Once we have the math books arranged, then we would arrange the 4 reference books within its section. All right, there are 4 factorial, or equivalently, 4 permute 4 ways to do that. And then finally, we would have to arrange or permute the history books. There are 5 of those. And so 5 factorial, or equivalently 5 permute 5 ways of doing that. And so by the fundamental rule of counting, the FRC, the number of ways of arranging the books subject to this constraint, where books of the same type must stay together, is the product of these numbers. 3 factorial times 3 factorial times 4 factorial times 5 factorial, which gives us 103,000 680. So that is the total number of ways of arranging the 12 books on the shelf, given that books of the same type must stay together. Now, that's a lot smaller than the total number of ways of arranging 12 books on the shelf without any constraints. And so you can see here that as we add constraints, we're going to be reducing the number of ways that we can perform a particular process. Okay, the last question in this example: in how many ways can the books be arranged on a shelf if books of the same type must stay together and the reference books must come first? All right, so again, we can think of this as a multi-step process. The first step in this case, at least the way I've arranged it, is to set the position of the reference book type. So the reference books have to come first, and so there's only one way to set the position of the reference books. All right, they're going to go first. Now, once we've set the position of the reference books, then we have to arrange the other two book types, the math books and the history books. And so because there are two remaining types, there are 2 factorial, or 2 permute 2 ways of doing that. Once we've arranged the types, then we again are going to arrange the books within each type. So there are 3 factorial ways to arrange the math books. There are 4 factorial ways to arrange the reference books within that type. And then there are 5 factorial ways of arranging the 5 history books within its type. And so by the fundamental rule of counting, the number of ways of arranging the books on a shelf within each type, if the reference books have to come first, is given by this product, which is 34,560. So again, adding a constraint, we reduce the number of ways that this process can be performed. And this slide just summarizes those calculations in a more succinct format. All right, we're going to stop the video here and pick up more examples in the next lecture video.